Now we will discuss subspace. So let V be a vector space over a field K. So V be a vector space over a field K and let W is a subset of V. Okay. Then W is a subspace of V if W itself a vector space with respect to the operations of vector addition and scalar multiplication on V. So however, if W is a subset of a vector space V, then some of the axioms automatically holds in W because they already hold in V. So there is a theorem whenever we have a subset that is W of a vector space V, then under which property or under which condition W will be subspace of the vector space V. So let us consider W is a subset of a vector space V, then W is a subspace or W will be subspace of V if the following two conditions hold. First of all, the zero vector belongs to W, and for every UV belongs to W and K belongs to that field, the sum will be contained in W and the scalar multiplication contained in W. So whenever you are given a subset of a vector space V, then if you are asking to show that W is a subspace or not, you have to check these two properties. So first of all, zero element is in the set W or not, you have to check that. And the second property, take any two element U and V from this W and K from the field K, then see U plus V is in the W or not. If in the W, then it's okay, and then check K into U. If this also in W, then we say that this W will be the subspace of the vector space V. And these two property, this 1 and 2 together imply that this for every UV belongs to W and AB belongs to K, the linear combination AU plus BV belongs to W. If this holds, then we say W is a subspace of V. Okay, over the same field K. So let us take some example. Consider that the vector space V R3 and let U consist of all vectors in R3 whose entries are equal. That is, let us define a set U that is subset of R3 in such a way that A, B, C are all equal. Okay, now we have to see that this U will be subspace of R3 or not. So for example, take this element 111 minus 333 and 777 minus 222 are vectors in U. Geometrically, U is a line through the origin. So 0 0 0 element, that is 0 element of R3, that is all elements are equal, so this belongs to U. And if you take any element U1, that can be written as A1 comma B1 comma C1, and U2 equal to A2 comma B2 comma C2, both belongs to U. Then from this you can conclude that A1 equal to B1 equal to C1, and from this A2 equal to B2 equal to C2, as both belongs to U. So therefore, if you find U1 plus U2, so this will give you A1 plus A2 comma B1 plus B2 comma C1 plus C2. So in this element, A1 plus A2 equal to 0, and this is also equal to, so not 0. So as these are all equal, so therefore this summation or sum will be equal. So therefore we can conclude that U is a subspace of R3. We will solve other question. So now we see the intersection of two vector space. Intersection of subspaces will be vector space or not. So let us consider U and V be two subspaces of a vector space V. So we show that the intersection is also a subspace of V. So as U and W are subspaces of V, okay, so 0 belongs to U and 0 belongs to W. So this implies that 0 belongs to U intersection W. So first condition is satisfied, that zero element will be in the subset, that is u intersection this. And second property, for second property we have to assume two element uv belongs to u and uv belongs to w. So from this we can conclude that, so no, first of all we have to prove u intersection w a vector space. So for that we choose u and v from this intersection. So this implies that u belongs to, that is small u belongs to u, and also u belongs to u and v belongs to u. So therefore, as u is a subspace, so u plus v belongs to u. Similarly, so from this we get v belongs to u and v belongs to w. So these both imply that, sorry, so u belongs to w, v belongs to w. So u comma v belongs to u intersection w implies that u contained in both u and w. So first we take, similarly v contained in both u and w. So first we take uv contained in u. So as u is a subspace of a vector space, so it will fulfill the condition to be a subspace. So u plus v also belongs to u. So similarly we take uv belongs to w, and this will imply that u plus v belongs to w. So from this u plus v belongs to u, that is 1, and this is u plus v belongs to w 2. So from 1 and 2 we get u plus v belongs to u intersection w. So first we take uv belongs to u intersection w. We prove that u plus v belongs to u intersection w. And one property remains, that is, if we take scalars k in k, then k into u will be in u intersection w. That is, if u belongs to, if you take u belongs to u intersection w, then u implies in this and in this, and so ku belongs to u and ku belongs to w. So this will imply ku belongs to this. So therefore we say u intersection w is subspace. So there is a theorem: the intersection of any number of subspaces of a vector space is a subspace. So here we take two subspaces, intersection of two subspaces is a vector space or subspace of a v. So we take u is a subspace of v, w is a subspace of v, then the intersection of u w is also a subspace of v. So here we take two subspace of v. So if we take any number of subspaces of a vector space v, then the intersection, that is intersection for I equal to 1 to n u I will be subspace of v, where each ui is a subspace of v. Okay, so intersection of any number of subspaces of vector space is a subspace. So that's it. If you like it, please subscribe my channel and share with your friends. It will help you. So I will discuss also previous year questions later when we complete this chapter theoretically.